Hello, Juan.
Hello. Hello,
How are
Gustavo.
you?
Fine, thanks. And you?
I'm fine
Busy.
too.
Busy.
Busy. Yes, it's been a ride, but we are close to the end now.
Yeah, yeah.
And thanks for being
Congratulations.
here. Yeah, thank you.
Congratulations. Very, very,
And
very interesting sessions.
yes, and we are happy that the team of Caesar has joined us this year in massively.
Yeah.
So that really adds to the conference. Okay, so we're just starting the time, waiting for the time to officially start. We have a new chairperson now. It will be Katan Kotari for chairing the final two workshops. We have Juan Vaquerizo, Juan Angel, and then later we'll have Michelle Faya. And I have to make you co-host so you can share your screen. Yes, I think we can start. So Katan, please do the honors.
Thanks, Gustavo, and for giving me the floor. Uh, so we have with us Juan Vaquerizo. Am I right? Okay.
Yeah.
From Spain, and he's going to present a workshop to us. The workshop is on looking for life in the universe, hands-on activities about astrobiology. He comes from a project named as Caesar Education Project from Spain. And the workshop aims to introduce astrobiology to classrooms focusing on study of life in the universe. Um, Really looking forward to the workshop, and the floor is yours. We do have an hour with us, and yeah.
Thank you. Thank you very much, Katan. I'm going to share my screen. First of all. Okay. Please let me see if you are seeing my screen.
We can see the screen, but not in the presentation mode. It's in the presentation mode, yes.
Okay. Okay, thank you very much, Katan, for your presentation, and thank you to the committee to accept all of our presentations. We are very glad to share with all of you our activities, and we are very happy to see how many people is working on our topics and our passion. And then it's my turn to share with you about the CSAR project, one of the activities that we are carry on, focusing on different aspects that you have already known about our project. Only in brief, just to mention that we are a joint project in partnership with the Space Agency, ESA, the INTA, the National Space and Technology Spanish institution, and then a technological company called SDEFE. And then in our main objectives, as we mentioned already in our previous presentations, is as all of you to foster interest in space science and technology and use real data in our classroom, to learn science by doing science, and try to foster scientific vocation also. And how we do this is in different aspects, in different categories. And some of them have been already shown to you in our previous presentation, and it's my turn to show you how we invite teachers to do these kind of topics in their classroom. Is by teacher training courses, national and international. In my case, I'm gonna show you how could you use this space science and astronomy and astrobiology in your classroom by some simple experiments. Okay, we are not doing live experiments because there is no way for you to get the material, but I want to show you how could be done by you a very simple way. But first, let me give you some general ideas about astrobiology. I'm sure that you know about astrobiology, but I need to put the big pictures in front of you before we start to doing things. Okay, and then we will work together and trying to do this kind of experiments, simple experiments, in this astrobiological way. I mean, you will know about them. Maybe you are aware of that kind of experiments, but we are trying to integrate them in a very, very big picture regarding astrobiology. Okay, so first of all, what is astrobiology? Okay, in brief, this is the study of life in the universe. We are using two of the big words in science: life as a phenomena and universe. So for us to bring these kind of topics to the classroom, we think that it's very, very interesting way, because it's a very big idea, the study of life in the universe, and we need to focus in some scientific aspects, not only spiritual or social or human aspects, but we need also to focus on science. So we need a hypothesis, and this is our astrobiological hypothesis. Is life as phenomenon is a consequence of a chemical evolution of the universe. So we need to know about chemistry, just to know how life can arise in a place in the universe. So that's our starting point. And how we do that? We do that in a very, very multidisciplinary approach. It means that all the sciences are welcome in the study of life in the universe. All the science, I mean all of them, in partial or crucial points of view, but all of them are more than welcome in this endeavor of knowing if life exists outside the Earth, on the universe. So in brief, we need to know, we need to have a comprehensive and integrated understanding of different levels. Local ones, biological, on Earth, in our planet. Planetary means in another places, another planets or moons, and then in a cosmic scale. So we need to know in our universe when is chemically ready in the universe, where is chemical ready for life to exist in a place, in an environment. Then we need to know about the environments, the conditions of the environment, and the habitable conditions for an environment. So we need to know about how can we know these conditions, how can we derive from these conditions the possibility for life to exist on that places, and things like that. More, we need to search for evidence of prebiotic chemistry. I mean, first of life, we need to have evolution life, chemistry, sorry. Before life, we need chemistry, evolved chemistry. So we need to know in what point we can go from chemistry, complex chemistry, to biology. So another kind of complex chemistry, but more than chemistry, is life. So we need to search for evidence of this evolution chemistry, complex chemistry, in the solar system and beyond, to know more about the environments. And some examples here: Europa and Ganymede, and Callisto, Jupiter moons, and Enceladus and Titan, Saturn moons, and also Mars, as you know. Behind me, you have Mars. And then we need also to make a research into the origins of life on Earth. We need to know as much as possible about life on Earth. We have only one example of life. So we need to know about life on Earth, its origin, its evolution, early evolution, and the diversity, nowadays, the big diversity of life on Earth. We need to know about that, just to know how to search outside. Okay, so we do that in several steps. Understanding what is life, it's a matter of chemistry, as you already know, but also about geology, because we need to know about the environments, and that's geology, and also physics. So geology, chemistry, physics means, after biology, we need to know all of these topics interrelated, just to know about the possibility for an environment to arbor life. And then we need to know the evolution of the universe in a chemistry from a chemistry point of view. We need to know how life is the last step in this ladder: galaxies, stars, planets, life. So we need to know at what point in time in the evolution of the universe life is ready to appear. And finally, we have a very strong arm to do this research, because we have a very I think we are ready to explore outside our limits, our boundaries, not only with our brains, but our imagination, but also with our technology. We have a very strong technological arm that allows us to pick this kind of data from the real places where life can exist right now. So the space and planetary exploration for us is crucial to have this possibility to study life outside it and to find it. And there are several steps. First, the origin of elements and molecules. If life is based on chemistry, we need to know about the elements and molecules, the origin. We know the origins of the different elements in our period table. And we know that we need to have the bricks ready to create life. So we need to know when the bricks are available for life to exist or to be created. So as you can see here, we need a lot of things about the chemical elements, and we know about the origin. But in the astrobiological point of view, we have only 6 of these elements available for life, or in terrestrial life, we only use 6 of these bricks. And for you to remember, this is this word, chomps, and carbon means carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These 6 elements creates all the living beings on Earth. So as you can see, there are a lot of more elements available for life or for any complex phenomena in the universe, but on Earth, only these 6 elements have been used for life, and having the possibility to use the rest of them, because all of these elements are available on Earth. But we don't know why life only uses these only 6 elements. Maybe in another places in the universe, maybe it could be possible to think about another kind of life, another kind of biochemistry based not only in these 6 elements, but in another elements. But we don't know how to search for that kind of phenomena right now, or maybe yes. So from molecules to life, we need to know about the biochemical pathways. You can see here the complexity of that endeavor, and we are working on it. Astrobiologists are working on it very hardly, because we know that first on Earth, we know that early Earth was exist without life. So at some point, life arose on that planet. So what kind of steps were done just to arrive to life? We think that first we need an habitable world. So we need the conditions that permits chemistry to evolve from simple chemistry, simple molecules, to complex molecules based on carbon in our case, and using water as a dissolvent, okay, a solvent. And we have these steps: prebiotic synthesis, polymers and vesicles, mean some kind of bags inside of which some kind of molecules can work together to bring these protocells, okay? And then we have LUCA. LUCA is an acronym meaning Last Universal Common Ancestor, and we think that this is the first organism living on Earth in the early stages of our planet. Maybe 3.8 billion years. So from that LUCA evolves the whole tree of life on Earth, this diversity that we have now on our planet. So that's are the steps that we need to know how and when it comes. So it's a very, very, very interesting challenge for scientists. We know about the limits of life, and we know this picture, the tree of life. In the center is LUCA, but you see here the diversity of life, and that's a very, very good point for us to know about the evolution of life. But there is a difficulty because we need to know the origin, and that's very, very difficult to reach because there are not so many information about LUCA right now. And this technological arm brings us the opportunity to explore all the environments in our solar system. All of the planets have been studied, a lot of moons of the planets. We are doing right now, ESA is exploring the solar system, and we have a lot of information. And we also have the cosmic observers to search for another worlds outside our solar system. So we have a lot of information about the environments, and we have a lot of ways to study this. We can search for extremophiles on Earth, as you can see here in the bottom right and the left, and we can also simulate environments that we are not able to reach with our sensors. So we can do simulating chambers, and we can also simulate phenomena like impact craters, just to know about this kind of phenomena in our solar system. And we can also study some kind of organisms on Earth. So that's the big picture, okay? So that's the way in which we could design our classes, science classes, regarding these kind of topics, okay? So astrobiology could be our big idea, okay, surrounding us, and all of our activities could be related with science, with different kind of sciences, and then try to push forward to study this astrobiological question that we are looking for answers in that theme. So just to a brief explanation of different kind of experiments that we could carry out with our students is, first of all, DNA extraction. This is a biology class classic experiment, but we can create a question. So we need to know about the existence of DNA in our sample. We can bring a sample from Mars or from our backyard or a place where we don't know if life is present in that sample, and we can carry out this procedure, this experiment, just to know the presence of DNA in the sample. And that means if DNA is present, that there is life in that sample. So we could search for life with this kind of experiment. If you invite your students to design a robotic way to do this experiment and put it on a spacecraft, we could send this to another planet, another place, and just to look for DNA in that places. And that's a very, very good question, not only regarding the biology, but also regarding astrobiology. So we can do this experiment. This is a classic one. We are using this detergent just to break membranes to access to the DNA, and then salt and sodium bicarbonate just to protect the DNA inside the cytoplasm, and then isolate the DNA molecules coming from the cells present on the sample, maybe on the sample, and with ethanol to isolate, okay? And the exact procedure, the protocol is like this, okay, take a volume of the sample and then mix it with the breaking membranes solution, and then mix it just to let the breaking membrane solution to break the cells, and then pick a sample of this, a volume of this, and then put it in contact with ethanol just to precipitate the DNA. At the end, you see the DNA. In the bottom part is the sample, in the upper part is the ethanol, and in the interface there is an accumulation of all of the DNA molecules present in every single cell in the sample, just to let you know that there is life present in that sample. This is the receipt of the breaking membrane solution, okay? And you can use this experiment just to not only to know about the DNA, but also to know about the extraction, the possibility to know about the presence of life in a sample, okay, coming from everywhere, okay? This is a YouTube link just to make you see, or to see this experiment in brief, explaining, but in Spanish, and you can see here the whole process, okay? And then we have also another possibility to do it in the DNA replication, another kind of process that is present in our living cells. And this is the DNA replication. We have the opportunity to explain this complex process by doing live with people, okay? So we can explain the presence of enzymes involved in this DNA replication. We have the opportunity to explain how it works, every single enzyme. We can, okay, make it like a category, the unzipper, the initializer, the gluer, or the builder. And the real names are these. And we can give these roles to people, and then another roles to another people just to be bases, okay, bases in the DNA, and then to invite the group to make this DNA replication, okay? Some of the people are bases in a existing DNA string, and then the enzymes are doing the work of replication of the molecule, okay? So we could explain life with people moving, with people doing things, with people feeling. I am an enzyme, I am a base on the DNA molecule, and then we can try to make it as a game. But it's a very interesting way to explain this kind of complex processes, because people is like playing a role, and this is very, very interesting. I think that we did that in some training courses, and it's very, very funny. And it's like a desire, maybe in a big place, in a school, to do it with I don't know, maybe starting with 100 people doing the first DNA string, and then finishing with 200 DNA strings, a lot of DNA bases around, and a lot of enzymes going around and organizing all the stuff. Okay, we did that, and you can see here with colored caps for the bases, and the white ones are the enzymes. Okay, we did adults, the bases. Okay, they are like their own business, nothing related with activity, and the white ones were kids. Okay, very responsible enzymes, taking the adults to put it on the right place. Okay, and it's very, very interesting because it's very funny, and it's a way to make accessible to students this DNA replication that is a very complex concept. Okay, so this is another idea. We can also do impact craters just to explain how is the process, the phenomena, because we only see the result of the crater. We didn't see the real impact. We didn't see the impact taking place. We only see the results. So we need to know about this kind of phenomena. And we have we have a lot of places in our solar systems and full of craters. So we could try to explain a simple model to try to know how is it going, but we need to simulate this, and this is a very, very interesting way, because there's a real simulation in a scientific chamber, and using a very, very, very step-by-step camera, okay, very big resolution, and you can see how is formed the crater. You can see the ejecta, okay, and you can see the material inside the crater falling down. So we can try to create a model to explain how is what is going on, and try to make relations between the size, the radius, the depth, the distance of the ejecta, and things like that. Okay, you can see here in there's a square here. If you see, you can see here the shape of the crater depending on the angle of the impact. This is a real simulation, okay, taking place in the Center for Astrobiology, and this is used by researchers to create models. But we could also do it. We can try to derive or deduce how what's going on there, and try to simulate. This is the real one. You can see the difference in color between the recent ejecta coming from the crater and the existing floor. The difference in color means the differences in composition, maybe. So we can also try to get information. This one is on Mars, and this is on the Moon. Okay, it's the same idea. The differences in color, the ejecta, and things like that. This is a real crater, comparing two images with a time span between them, and you can see in the Moon how far the ejecta goes because of the lack of gravitational force. So the ejecta goes far away. Okay, and you can try to invite your students to do that in a very simple way, but we are able to do that. We can use flour, differences in composition, maybe cocoa and flour, and then try to simulate these impact craters. And we can do it like on the researchers did. We can use a camera. We can use also this and a repetition of the image just to know about the ejecta, the direction, the depth. And you can see here that sometimes the images of the craters resembles very well the reality. Okay, there is not the same idea, but we can try to get information about the phenomena, and it's very, very interesting way to do that. We have also the opportunity to study the water on Mars. We know about Mars a lot. We know all the planet. We map all the planet. We know better our Mars than our own planet, and we know that we are sending, and we have a lot of missions that have landed there in the Martian surface, and we know that water, liquid water, was present on the early Mars. We know that because we have a lot of images from orbit or from the surface that we can see these water beds dry now, but water beds and rivers and things like that, like these river fans and things like that. So we know that water, liquid water, was once on Mars surface. So we need to know why there is no liquid water now on Mars, because there is a lot of water, but why there is no liquid water. And we we know that because it's the lack of pressure. Okay. I don't know if you are listening. Maybe not.
It's not audible. It's not audible.
No problem. No problem because it's in Spanish. You can see here. You can make water change the phase from liquid to water to vapor without not using temperature but pressure. So you are able to change the pressure inside your cylinder, and then by doing that, you are going down the pressure inside the cylinder, and that's the reason why the water is changing phase from liquid water to vapor. So that's why on Mars now, because of this very, very low atmospheric pressure, water on Mars is only on ice state or on vapor state. There is no possibility for water to exist in liquid state now on Mars surface. But in the past, we know that existence of liquid water. So we know that in the past, the atmosphere, the Martian atmosphere was thicker and denser because we know that the water was liquid in that time. Okay, so we can try this kind of experiments, and we can use it also a vacuum chamber. Okay, because this is easier because inside the vacuum chamber you can put your liquid water, and inside the glass of liquid water you can put a thermometer, and then you can check that the temperature is constant. But when you are making the vacuum on the chamber, the water is boiling. It's like boiling, it's passing to vapor, but the temperature is constant, is the ambient temperature. So there is no way for water to change phase because of the growing temperature, but by the going down the pressure. Okay, and that's very, very interesting because you can see the phenomenon, the effect directly. Okay, so for students, that is a very, very interesting way of thinking. And we can also try to study another worlds, okay? Activities about exoplanets. There is a lot of things that we can do about exoplanets. We know that we have a lot of exoplanet hunters, and in our future, in our next future, there are a lot of missions like Plato and Ariel, and a lot of also space telescopes coming in the coming years. So we have a lot of information about the exoplanets. We know about the exoplanets. We have categories of exoplanets. Terrestrial gas giants are very known. Neptune-like. We are quite similar our solar system, but we have super Earth. We are between the Earth and Neptune. Okay, and also we have it's called hot Jupiters. It means that gas giants, but very, very close to the host star. So the temperature is very high. So we have these kind of things coming around everywhere in the media. We have a lot of images like these of the exoplanets, but believe me, they are all fake. We didn't have these kind of images. This is only imagination. We have data about the planets. Maybe this is a gas planet, or maybe this is a terrestrial planet. But if I know about the terrestrial planet, I know the density, but I don't know if there is water, liquid water in the surface or not. Maybe if I know some more about the exoplanet atmosphere, we can infer some kind of information about the presence of water, liquid water on the surface, but there is no direct information about that. So all of these images are imagination, all of them. So why don't imagine exoplanets also with the students? We can give them information about the data we have gathering from these exoplanets, and then make them imagine the exoplanet, like a graphic designer do right now when we are trying to make a press release regarding some discovery. The graphic designers are having information from the researchers, from the scientists, but then they are doing like a kind of imagination playing. So we can imagine exoplanets or we can try to make this kind of quest to people. These are 9 images. One of them is a moon, and the rest are frying pans. Can you pick the right one? The right moon is on the central row on the left. This is Europa. Europa is a Jupiter moon. The rest, the other 8 images, are frying pans. Okay, so the imagination is very, 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 very strong. And we can imagine, I don't know, icy moons here, icy places, or oceanic worlds, or things like that, okay? So why not make students imagine their own worlds, okay? Having information about them, but then let's get them play with their imagination, okay? And imagine worlds like this, okay? Or maybe to do it in a 3D way, okay? More tactile for people impaired, and it's very, very interesting, okay? This is very, very, very funny. All of them with their own exoplanet. Imagine exoplanet with their name, the position, and the constellation in which is located, and things like that, okay? Or maybe do it in a 3D mode. Okay, try to do it in a 3D with the 3D printer in a 3D model. Okay, spherical mode, or maybe in a 2-dimension, like a surface. Okay, and that is very interesting because we can use it with a tactile dimension. So impaired people could know about the presence of craters or things like the water beds and things like that, okay? So it's very, very interesting way also to imagine another places, another environments. Or we can simulate cryovolcanoes in these kind of icy moons that we know, like this, Europa, this, Ganymede, this, Callisto, or this, Enceladus. This is from Saturn, and the other ones are from Jupiter. These are icy moons. Means that the surface is ice, water ice, but underneath the surface, there are big amounts of liquid water inside. And we know about that because of these plumes, gas plumes that are going outside from these fractures or these volcanoes. And because of the low temperature of this phenomena, this is called cryovolcano. Means in a low temperature mode. So there is no melting rock, but it's liquid water. But there is no solid rock, but there is ice water. And in that kind of parallelism, this is called cryovolcanoes. And we can simulate cryovolcanoes, okay? We can do it using dry ice. We can try to do it always with security because it's very, very low temperature. The dry ice is like 80 degrees below zero. So we have to use always gloves. And you can see the sublimation when you are growing the temperature. And we are using this dry ice to simulate the ocean underneath, and this water color to put it in contact with the dry ice, just to create the ice cover, the ice surface on the dry ice. So when the liquid water contacts the dry ice, freezes, and it creates a water ice surface closing the sublimation of the dry ice. So where the dry ice reach to broke the dry surface, the ice surface creates these bubbles. These are the cryovolcanoes. Every single volume of bubbles means a gas plume, okay, going outside the icy surface. in this icy surface, we are creating cryovolcanoes. Okay, this is a cryovolcano. You can do it for your classroom, just to try to make them understand about this phenomena. Okay, this is called cryovolcanism. This is a very, very interesting way of try to make understand some kind of phenomena. And we have also the opportunity to study cosmic dust. Okay, we have a lot of projects and about this, but we can also use it inside of this kind of a lot of experiments available for us to try to understand things about astrobiology. This cosmic dust is the hunt for micrometeorites. It's a very, very interesting way of studying these phenomena. Okay, these different names for the same object, depending on this is coming from outside, this is entering our atmosphere, and this is at the end remaining some solid remainings on our surface. Okay, this is the difference between meteor, fireballs, and meteorite. Okay, but these are the same object depending on the position. Okay, we can try to search for these, and we need only a microscope and a magnet. Okay, and some ideas. But the idea is to get dirt, because they are coming every single moment. They are coming this material on Earth, so we only need to have some space that there is receiving this material, and the roof of our schools are perfect, because these are perfect places, because they are receiving every single moment this material. So at some point we have the opportunity to go up and to take this dirt, or we can wait for the rain to come and to help us to go down all this dirt. So we have to wait for a rainy day, and after this rainy day we can check for the presence of this dirt if we use this kind of now a receipt. But first I need to point out that flat roofs are better than the ground, because on the ground there are a lot of contaminants, and we are working with these contaminants. So it's better to use these kind of places, okay, in order to avoid this presence of contaminants. Okay, so we can design for every single school, we can design for our downspout in our school, our downspout, we can design this micrometer collector. Okay, we can design for our school, we can print it with a 3D printer, and we can use a magnet in the low part. This is like an U shape. Okay, inside this is a U shape, and in the bottom part of the U we can put a big magnet. So when the water is going down, the dirt, magnetic dirt, is attaching in the low part of the U. So when these are, I don't know, after 1 or 2 days of rainy days, we can go there and we can check the presence of a lot of dirt in this, and then go to the classroom with this dirt just to analyze. Okay, so it's a very, very interesting way to work, because it's involved all the school or the classes, and we have to design the micrometer trap, we have to design the protocols and the classes, and it's very, very interesting. And then we can use this magnet also, not only this one of the micrometeorite trap, but also another magnets for us in a bag, just to collect this material. Okay, just to separate. And the idea of the plastic bag is to easily separate, because if not, it's attached to the magnet, that is quite difficult to separate them. So you use the plastic bag, and then we put out the magnet and remain the dirt, the magnetic dirt, and then we use the microscope. Okay, we are using this on the picture is a Bluetooth microscope. It's very, very not so expensive, like, I don't know, $50, €50, and you can buy it very easily. And this is like Bluetooth. You can see the cell phone. You can see the image on the cell phone or on the laptop. You can use it everywhere with this Bluetooth connection. So we can check for micrometeorites. These are the sizes of the micrometeorites. I mean, usually 0.2 millimeters. So they are very tiny. So there is no way to a very big magnetic ball to be a micrometeorite. This is a meteorite itself, but this kind of micrometeorites that we are looking for. Okay, when we think, sorry, that we have a micrometeorite, sorry, we need to check it with a electronic microscope. There is no way with our Bluetooth microscope to discover a micrometeorite, to ensure that we have found a micrometeorite. We need the confirmation using an electronic microscope, and these are the images with these electronic microscopes. Okay, these are real micrometeorites, but we need that confirmation. But when we have this confirmation, we have discovered a micrometeorite. Okay, so this is a very interesting way of work with the students, because there is a lot of involving topics and people and teams. So it's very, very interesting to get involved all the school. And for like my ending experiment is a project that we have already talked about 2 years ago about this project. Is communicating with other lives. We think that this could be interesting to send a message to an exoplanet, because they are involving astrobiology, exoplanets and habitability, and also SERI project. Okay, they are playing some kind of different topics, but we think that this is very interesting for students to get involved in this kind of projects. And really fast, really quick overview of this, because we have already have information. This is a pictogram. We have a context. We are inviting a group of students with a teacher to create a pictogram, the 73x73 size, just to put information about us to another intelligent civilization. Okay, and this was we have only one edition last year, and this was the winning pictogram. Okay, this was the selected, and on the right part the explanation. Okay, we are explaining about our Tea Garden B was the planet, the objective. So it's information about the Earth, the Tea Garden B, and also our galaxy, our position, relative positions, and something related with us, our cells, our regarding a water molecule, and our humans, intelligent and capable of communicating human being or human livings. Okay, this was the antenna, and this was the target. Okay, Tea Garden B, and this is very, very interesting project, because there is a lot of work that could be done regarding technology, regarding life, regarding intelligence, and regarding all of these things working together, just to try to send a message to another place where we don't know exactly how intelligent are they. And it was very, very interesting. And this year is the second edition, and we think that it's a very good idea to be done everywhere, because there is only a need of an antenna with the capacity to send a message. Okay, and if you have some needs or some advice, we are here to help you if you need to. And I think that's all for my part. Thank you very much. And if you have some questions, I'm glad to answer them.
I think
Thank you.
it was a wonderful presentation. And it was actually not one workshop, it was many workshops which you gave us. So yeah, thank you for this wonderful resources which you have shared. I see a message someone wanted to leave in between, but has shared by Joy Oluwalia. that it was wonderful, and some claps. But I think it would be also interesting. Most of the things which you have shared is more physical in nature. So, and very, very tactile in nature. So I really enjoyed the way you were explaining, and most of the procedures were very clear. Yeah.
Yeah, these
Gustavo,
are. We usually do these kind of things with teachers in our training workshops, in our training courses, and we do this kind of experiment that I showed you in live mode. I mean, we bring the material and we carry out the experiments. But the idea for this workshop is because of the lack of the possibility to people attending to get all the material ready to do it, and the lack of time. It was my idea to just to show how is it done, because every single teacher that sees this kind of experiment knows quickly how to do it, and it's very, very clear for them, because them are very familiar with these kind of things, activities, times, spaces, and that's the idea of this workshop, doing in that way without material in hands. Okay.
I really loved the frying pan one. Okay. I really don't see many questions. Gustavo, do you have any question? Do you want to
Yes,
share
I
some?
wanted to ask Juan, what is the easiest way for the people who are watching this to get more information about the materials, the procedures, to execute each one of those activities? Are these all in one single place? So if you can share the link, that
Okay.
would be really useful for people who are watching this now or later.
Okay, we are now working on our new CSAR website, and there we are planning to put this information regarding this workshop. But by now, if you have some questions or needs or advice, just let me know through this. This is my email, and just let me know. I will be glad to share with you and help in any way for my part. Okay.
It's a very funny thing. We have been using dry ice for freezing soap bubbles since almost past 2 years, but we never imagined that it can be used to explain astronomy. And I think that's what we are going to start doing. So yeah, thank you for this wonderful set of resources. And whosoever wants to get in touch with Juan, they can surely write on this email address. I'm going to take a copy of the same for my reference.
Okay,
And
I'll put it also in the chat.
in the chat, yeah.
Okay.
And yeah, and we are
Perfect.
Gustavo.
Yes,
Do
Michelle
have
is here. I think we
yeah, I can
can,
see this.
since it's the last one, I think we can start a bit earlier. So I think nobody will oppose that.